Hi, this is Math 2231, remote delivery for Mother's Day, May 10th. The topic is numerical integration. We're going to talk about the trapezoidal rule and Simpson's rule and use this device to throttle the presentation and maximize your understanding. Unfortunately, some integrals are important, like this one, very common in applied math, but we cannot use the fundamental theorem of calculus to evaluate this. There is no use substitution that will work, and we cannot find a function that is the antiderivative of this expression. That's where numerical integration comes in, and that's our topic for the day. First, we're going to talk about the trapezoidal rule. So we break up the interval of integration, a to b, into n subintervals of equal width. That means that these are delta x is equal to b minus a over n. And then on each subinterval, we approximate the function with a straight line that is equal to the function values at either endpoint of the interval. So you see we're drawing straight lines and getting the green area to approximate the area that is underneath the red curve. Now it turns out that each of these geometrical figures is a trapezoid. So this is the trapezoidal rule. And this does a pretty good job of approximating the area. Let's look at how this will work. You see the area of each of the trapezoids is going to be the height of the trapezoid divided by 2 times the sum of the bases. So if we use all of them, we're going to add up all these thank goodness for trapezoids. And if we reorganize this, what we're going to see is that, for example, f of x sub 1 appears here, but it also appears here. So we're going to get this kind of nice patterned formula. So this integral is approximately equal to, that is delta x divided by 2, and the pattern is the coefficient here is 1, the coefficient here is 1, but all of those in between have coefficients of 2. This is the trapezoidal rule. Note that as n tends to infinity, this approximation gets closer and closer to the actual numerical value. It's good enough to do engineering with. I'm going to talk about Simpson's rule just a little bit now. In the trapezoidal rule, we approximated the curve with a straight line and got trapezoids. In Simpson's rule, we approximate the function with a parabola, and that means we will have to have an even number of points. And here's an example where we're doing that. So you see the parabola that will go through here is we'll get 3 points like that. So you see these two are kind of conjoined, these are conjoined, and these are conjoined. When we do that kind of calculation with the same definition for delta x, we get the trapezoidal rule tells us that the integral from a to b of f of x dx is approximately equal to, it is delta x over 3. And the pattern is you have a 1 here, you have a 1 here. Then you alternate 4s and 2s. 4, 2, 4, 2, 4, 2, 2, 4, and then 1 again. Note as n tends to infinity, this approximation gets closer and closer to the actual numerical value. Let's look at an example. For n equal 4, we'll approximate the integral that we started with. Now in either case, delta x is going to be the length of this interval, 2 minus 0, divided by how many n we have. So it's going to be 1/2. So these are the subintervals. So for the trapezoidal rule, we get delta x over 2. Here's the pattern, 1, 2, 2, 2, and 1 again. And we do the calculation and we get this approximation. For Simpson's rule, it is delta x, but now over 3. The pattern is 1, 4, 2, 4, 1, and we get this number. There also are very strong error estimates for this, and so if the second derivative is bounded by above by k, an absolute value, and the fourth derivative is bounded above by m for all a less than or equal to x, less than or equal to b, then this is the maximum error that you make with the trapezoidal rule, is bounded above by that in absolute value. The maximum error of Simpson's rule is here. Notice that 12 is a smaller number than 180, and n squared is a smaller number than n to the fourth, so the Simpson's rule is a tighter estimate, a little harder to use. Okay, now this numerical integration is not on the final, just like hyperbolic trig functions are not on the final, but we did cover them, and this is on the recovery quiz, which many of you will be interested in. So now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless.